Have you ever watched a clip from orbit where an astronaut lets go of a tool and it just keeps going? Open space, sparse stars, long, quiet paths, nothing pushes, nothing pulls, yet motion stays. It feels odd, only because daily life on Earth hides what's really at work. Out here, the rule stands out. Start moving, and you keep moving until something gets in the way. That simple idea bends flight plans, holds satellites on track, and turns small nudges into long journeys. We'll pull on that thread and see what falls into place, step by step. If this kind of space science clicks for you, tap like and subscribe so you won't miss the next chapter. Now, let's open the door to inertia, the hidden law that keeps motion going. Picture a quiet rink and a sheet of clean, hard ice. A hockey puck rests on the surface, still and balanced. Nothing seems to act on it, so it stays put. This is not preference or mood. It is inertia, the tendency of an object to keep its current state of rest or motion unless a force changes it. A small push fixes that state. With a light tap, the puck slides. On clean ice, it would keep sliding, the speed steady and the direction straight, until friction from the ice, a bit of air drag, or the board supplies a force to slow it or turn it. Inertia does not supply motion or stop it. It preserves whatever state exists, whether rest or movement. Isaac Newton wrote this as the first law of motion. An object at rest stays at rest, and an object in motion keeps moving at constant velocity, unless acted upon by a net external force. Velocity here means speed with a direction. External force means a push or pull from outside the object, friction from the ice, the pull of gravity, the grip of your hand, the drag of air. The law sounds simple because it is a clear rule about how the world behaves when nothing gets in the way. Earlier ideas about motion were different. Aristotle, a major thinker of ancient Greece, taught that motion needed a continuous cause. In that view, a cart moved only while something kept pulling it, and a thrown stone continued because the air behind it pushed it along. This made sense to the eye in a world full of rough surfaces and thick air. Objects usually do slow down after a push, so it feels natural to think they require a steady cause. The trouble is that friction and drag hide the deeper rule. Once you reduce those effects, a new pattern appears. Galileo began to reveal that pattern. He studied rolling balls and smooth ramps, and noted that a ball allowed to move without much friction kept its speed. If the surface were perfectly smooth and flat, there would be no reason for the ball to stop. He reasoned that it would continue forever unless something interfered. Newton organized these insights into a full set of laws. Together they describe how forces change motion and how, in the absence of forces or when forces cancel, motion simply continues unchanged. Daily life shows the first law in simple ways. When a car slows quickly, your body leans forward. Your body was moving with the car. When the car slows, your body tends to keep its earlier motion. A seatbelt provides the force to bring you safely to the new state. When a bus starts from a stop, a bag on the seat may tip backward because the bus moves ahead while the bag's inertia keeps it at its earlier rest. A drink may slosh to the side during a turn because the cup turns with the car, but the liquid's inertia resists the change in direction until the cup's walls provide the force. Spaceflight makes inertia plain because there is so little friction. After a spacecraft finishes a burn and shuts off its engines, it does not slow down, it coasts. Its path and speed change only when gravity from a planet bends its course. When thrusters fire, or when it passes through thin gas and dust. Satellites in low Earth orbit circle the planet for many months or years because their horizontal speed and the pull of gravity form a steady balance. Gravity constantly changes their direction toward Earth, but there is little air at high altitude to slow them quickly. In higher orbits with less drag, satellites need only small adjustments over long periods. The same rule shapes trajectories between worlds. A short burn can set up a long cruise. Inertia does not choose rest over motion or motion over rest. It treats both the same. If an object is at rest, it stays at rest until a net force acts. If an object is moving, it keeps its velocity until a net force acts. This symmetry is easy to miss because our surroundings are full of forces. Ice still has some friction. Floors push up. Air pushes back. Wheels grip roads. These constant interactions change motion all the time. Reduce them, and the uniform behavior stands out. The first law anchors the rest of classical mechanics. It sets the stage for Newton's second law, which tells how forces change velocity, and for the third law, which links forces between interacting bodies. Without the first law, it would be hard to define a frame of reference where motion can be measured cleanly. The law also clarifies why many systems need steady input to fight losses. A plane needs engines, not to keep motion alive in empty space, but to overcome drag in air and to create lift. A bicycle is stable while moving because small steering corrections and the spinning wheels help keep its orientation. As it slows and friction dominates, those stabilizing effects fade, and it can tip. Older explanations of motion had limits because people had no way to strip away friction and observe the core behavior. Aristotle also separated the sky from Earth. He taught that the heavens were perfect and circular, while the earthly realm was messy and straight. Planets and stars were thought to move in circles because that was their natural mode. Earthly objects sought their natural place. Heavy things went down. Light things like fire went up. This neat map differed from what careful measurements eventually showed. When observation improved and tools like telescopes and smooth surfaces appeared, the same rules began to explain both realms. A famous example involves falling objects. It looks as if heavier things fall faster than lighter ones. In air, a hammer does reach the ground before a feather, but air resistance is the cause, not mass alone. In a vacuum, without air drag, objects near Earth accelerate downward at the same rate, regardless of mass, until forces like buoyancy or shape-dependent drag appear. On the Moon, where there is effectively no air, a hammer and a feather fall together. What seems obvious in air can mislead. Remove air, and a different truth becomes visible. Another older idea tried to explain continued motion by having the medium push from behind. This impetus picture tried to save the sense that an object needs a continuing cause, but it struggles in thin air or space. A ball thrown in a near vacuum keeps moving because nothing significant slows it. There is no helpful gust pushing it along. The simpler rule, no net force, no change in velocity fits all cases, from slow carts to fast spacecraft. The first law uses ordinary words but hides careful definitions. Force is any interaction that can change velocity. Contact forces like pushes and pulls, friction and tension, normal forces from surfaces, and long-range forces like gravity and electromagnetic forces. Net means the sum of all these forces, taking direction into account. If forces balance exactly, the net is zero, and the velocity stays as it is. If they do not, the object speeds up, slows down, or turns. Inertia is the resistance to changes in velocity. Mass measures how much inertia an object has. Double the mass and, for the same force, the change in velocity is half as much. These ideas combine to explain stable orbits. A planet keeps moving forward while gravity bends its path inward. The forward motion would carry it straight. Gravity gives a constant sideways pull, changing direction without changing speed much when the orbit is nearly circular. No fuel is needed to keep it moving once the speed and height are set. Thrusters are used only to adjust the speed or path, or to fight small drags. The same picture explains why a probe can use a gravity assist at a planet. The planet's pull changes the probe's direction and speed relative to the Sun without the probe using much fuel, because gravity provides the force during the flyby. Back on Earth, friction and drag are always nearby. Sliding surfaces rub and turn motion into heat. Wheels reduce friction by rolling, but bearings still resist motion. Air presses on moving things. Streamlining guides air smoothly around edges and lowers the drag. These details matter for engineering, yet the baseline remains. Once forces are known, motion follows the laws in a predictable way. Remove or balance the forces, and inertia carries the state forward unchanged. The path from Aristotle to Galileo to Newton shows how science advances. First comes a picture that fits common experience, but mixes cause and effect. Then come measurements that do not fit the old picture. Finally, a simpler rule appears that explains both the everyday case with friction and the special case without it. The new rule does not ignore experience. It explains why the old view felt right in some settings and failed in others. Inertia survived this test and now sits at the core of how we think about motion. It helps to keep the language plain. Objects do not want to move or to stop. They do not carry purposes. They respond to forces, and they keep their state when forces cancel. This is why a carefully balanced object can sit still for a long time, and why a satellite can circle for a long time. This is why a gentle push can send a puck gliding over smooth ice, and why it will slow on rough ice. This is why cargo shifts in a truck when the driver brakes, and why tying it down with straps forces keeps it in place. Seen this way, stillness and motion are two versions of the same rule. On a rink, small friction and minor bumps still act, so sliding slowly fades. In orbit, friction is tiny, so motion lasts and rest is rare. The law treats both states with the same calm rule. That is the strength of inertia. It makes no special cases until a force appears, and then it yields the same clear account of what happens next. Aristotle pictured water flowing downhill not only because gravity pulled it, but because down was its natural place. In that picture, motion and rest were guided by where things belonged. It gave the world a tidy order, yet it folded purpose into physics. The gaps were always there. Consider a rock rolling across the ground. If you stop pushing, Aristotle's view says the rock should stop at once. In practice, the rock keeps going for a short distance and only then settles. The push did not vanish. It was countered by other forces. Friction at the contact points and bumps in the path sap the motion and convert it to heat and small jolts. Without those losses, the rock would continue. Earth hides this deeper rule because friction is common and air resistance is everywhere. Most moving objects rub, scrape, or plow through air, so their motion fades. It is easy to draw the wrong lesson and think motion needs a constant cause. For a long time, there was no simple way to remove the interfering effects. Smooth bearings, air tracks, vacuum chambers, and precise timers did not exist. Older observers had to rely on rough materials and the quick timing of the eye. Under those limits, Aristotle's ideas held on, taught in universities, and woven into broader theories about place and purpose. As methods improved, careful observation began to peel away the confusion. The old model of crystalline spheres carrying planets did not match the data. Arrows flown from a bow traveled long distances with no wind pushing from behind. Stones rolled farther on smoother ground. The world did not follow the story of intent. It followed consistent rules. It is also fair to remember what Aristotle did get right. He tried to explain nature without appeals to magic, using logic and pattern. Even when his answers missed the mark, the act of asking clear questions pushed inquiry forward and set a platform for later progress. Ideas evolve. A proposal gains speed, meets resistance, and gets reshaped by new evidence. In that sense, the path from Aristotle to Galileo to Newton is a chain where each link matters. Galileo's link was built from experiments. He slowed motion down to see it clearly. Instead of watching objects fall too fast for the eye, he rolled spheres down inclined planes. A gentler slope meant the same physics played out over more time, and timing became possible with pendulums and water clocks. This was a practical way to strip away distractions. Galileo noticed a pattern. A ball rolling down one slope and up another tends to climb back to the same height from which it started. Make the second slope steeper or gentler. The ball still aims for the original level if friction is small. Extend the second slope so it is longer and less steep, and the ball travels farther to reach that same height. Push the idea one step further, let the second slope be perfectly flat, and there is no uphill to climb. In that ideal case, the ball would keep rolling without end. This is the core of inertia. Motion persists at constant speed in a straight line, unless a force changes it. The insight was simple yet sharp, because it named the real culprit behind everyday slowing: friction. Friction is a contact force between surfaces. At the microscopic level, surfaces are not perfectly smooth. Tiny ridges and pits interlock and drag against each other. As the object moves, those irregularities press, slip, and generate heat. Energy leaves the organized motion and becomes thermal energy in the materials. Even rolling objects face resistance in their bearings and at the small deformations where rubber meets the ground. Add air resistance, another force that grows with speed and surface area, and the slowdown is stronger. None of this means motion wants to end. It means forces are acting to change the velocity. Galileo did not have vacuum pumps or air bearings, but he reduced resistance enough to see the rule emerge. The smoother the ramp, the farther the roll. The gentler the slope, the closer to forever, the motion extended. He also analyzed falling bodies. The story of dropping spheres from the Leaning Tower of Pisa is likely legend, but the conclusion was sound. In the absence of air resistance, objects near Earth accelerate at the same rate, regardless of mass. What looks like heavier falls faster in air is mostly about drag, acting more effectively on light, wide objects like feathers. Remove the air, and the mismatch disappears. Galileo built more than results. He built a method. Ask a clear question, isolate the effect, measure carefully, and check the result again. Use a model to predict, and then test the prediction. Repeat. This approach allowed future scientists to extend his work with better tools. It also reached into the sky. With a telescope, Galileo saw moons orbiting Jupiter. That was direct evidence that not everything circled Earth. He saw sunspots marking change on the sun, a reminder that the heavens were not perfect. Together with careful measurements of planetary positions, these observations supported a view in which the same physical rules applied both on Earth and in the sky. Newton gathered these threads and expressed them with precise definitions. His first law states, "An object at rest remains at rest, and an object in motion continues in a straight line at a constant speed, unless acted upon by a net external force." Net means the sum of all forces, including their directions. If forces cancel, the net is zero and the velocity does not change. If forces do not cancel, velocity changes, speed increases or decreases, or direction turns. Velocity is speed with a direction. Changing either part is a change in velocity. The law does not cause motion to start or stop. It states what happens when nothing net acts. This law can be hard to see on Earth because most situations include forces. A toy car slows not because motion fades by itself, but because wheel friction, axle friction, rolling resistance, and air drag act together as an opposing net force. On smooth ice, a hockey puck slides much farther because friction is small, yet it still slows over time for the same reasons, just more gently. These examples are not exceptions to the law, they are the law. Once you account for the forces, spaceflight presents the pure form. After a spacecraft finishes a burn, it coasts. The engines shut down, yet its velocity continues. The path curves near planets because gravity provides a steady sideways pull, changing direction. In low Earth orbit, a small amount of atmospheric drag still remains, so stations like the ISS need periodic reboosts to maintain altitude. In higher orbits, the drag is tiny, and satellites can keep their paths with only rare adjustments for station keeping. Probes to the outer planets often use gravity assists, fly past a planet on a carefully chosen path, and gravity provides the force that redirects the probe and changes its speed relative to the Sunday. No continuous thrust is required. The planet's pull during the encounter does the work. The first law also gives a clean stage for measuring forces and accelerations, which is formalized in the second law. It guides how we think about frames of reference coordinate systems that move at constant velocity relative to each other. In such frames, the first law holds in the same form. This is why a passenger in a smoothly moving train, far from curves and vibrations, can toss a ball straight up and catch it at the same spot. The car's uniform motion does not need a special additional cause. The ball keeps the train's forward speed while it moves up and down relative to the passenger. Returning to the historical trail clarifies why Newton's statement was needed. The older impetus idea tried to keep a notion of stored push in the object. That picture helped explain why motion continued, but it could not make consistent predictions across different media. It also made a wrong promise. It suggested something extra had to be added to maintain motion. Newton's view is cleaner. No net force, no change in velocity. Add a net force, and the change depends on the force and the mass. Mass is the measure of inertia. Two objects pushed by the same force change their velocities by different amounts if their masses differ. Double the mass, and for the same force, the change in velocity per unit time is halved. This relation becomes the core of the second law, and ties the first law tightly to measurement. It also connects with energy use in technology. A plane must produce thrust to balance drag, and must create lift to balance weight. The engines do not keep motion alive in empty space. They overcome the real, measurable forces of air and gravity. A bicycle remains easier to balance at speed because small steering corrections combined with wheel rotation stabilize it. As speed drops and frictional effects dominate, those stabilizing effects weaken and tipping becomes likely. In space science, the first law is part of every mission plan. Trajectory designers calculate burns so that a short period of thrust sets up months of coasting. The Voyager probes cross the outer planets by linking gravity assists, each encounter providing the needed force to retarget the path. Small course correction burns trim the route when tiny forces like uneven solar pressure on the spacecraft accumulate over time. In orbit design, engineers choose altitudes where drag is low enough for the mission lifetime. For Earth observation at low altitudes, they plan fuel for periodic reboosts. For geostationary satellites, they plan small station-keeping maneuvers to counter tugs from the Sun and Moon and slight deviations in Earth's gravity. Back on the ground, a few controlled setups bring the law into view. Air tracks, float gliders, on a thin cushion of air to reduce friction, letting them keep speed for long distances on lab benches. Superconducting maglev systems remove contact between track and vehicle, so only air drag remains. Inside a vacuum tube, even that drag drops, and motion persists with very small losses. These systems are not about cheating nature. They are about removing specific forces, so the baseline behavior is visible. The shift from Aristotle to Galileo to Newton is not a story of sudden replacement, but of refinement. Each step removed a layer of confusion created by unrecognized forces. The picture that remains is stable and modest. Rest and motion are both natural when no net force acts. Changes in motion have specific causes. Measure the forces and you can predict the motion. This modest picture is powerful. It organizes everything from sliding pucks to orbiting moons with the same rule set. It is useful to keep the language plain. Water flows downhill because gravity provides a component of force along the slope, not because water belongs there. A cart stops because rolling resistance and bearing friction take energy from its motion, and air pushes back, not because motion runs out. A feather falls slowly in air because drag on a wide, light object is large compared to its weight. Remove the air, and the feather falls with the same acceleration as a hammer. A satellite in orbit does not need continuous pushing. It needs the right initial velocity and altitude, so gravity bends its path into a closed loop. Seen across these examples, the common thread is the same. Identify the forces, sum them to find the net, and then expect velocity to change only when that net is not zero. In quiet conditions, where forces balance or are absent, motion or rest simply continues. Where forces are present, motion changes in clear, measurable ways. This consistency is why the first law sits at the base of classical mechanics, and why it remains in every calculation of paths on Earth and in space. Imagine a place with no friction to slow you, no breeze to push back, no surface roughness to steal energy. In deep space, a toy car given a push would not coast and fade. It would keep its speed and direction. That is the clean form of Newton's first law. Motion continues unchanged when no net force acts. The other side of the law is just as important. Rest continues. 2. This part feels familiar. A body at rest needs a cause to change its state. In physics, a rock on the ground stays where it is until a force acts a push, a pull, or gravity along a slope. Without that, the rock remains still. Mass sits at the center of this behavior. Mass is not just how heavy something feels. Weight depends on gravity. Mass measures how much resistance to changes in motion an object has. That resistance is inertia. Put a ping pong ball and a bowling ball side by side. Both can sit still. Try to push them with the same effort. The ping pong ball moves easily. The bowling ball resists. That is inertia tied to mass. The same shows up when stopping objects. Once the bowling ball is rolling, slowing it takes effort. The push to reduce its speed mirrors the push needed to start it. Large mass means large resistance to any change. Momentum joins the picture. Momentum equals mass times velocity. Velocity is speed with direction. A larger mass or a higher speed gives more momentum. The more momentum, the harder it is to change course or speed. This is why ships need wide turns and long distances to stop. The ship's mass and speed give it significant momentum, and the forces available rudder forces through water. Engine thrust in reverse must work over time to change that momentum. In everyday terms, inertia resists change. Momentum measures motion that has to be redirected. The first law fits cleanly with the rest of mechanics. It sets a baseline. Change requires cause. Rest and motion are both natural states. Neither is favored. Neither is special. Forces make the difference. A soccer ball moves when you kick it because your foot applies a force large enough to overcome its inertia and any friction on the grass. A car that strikes a strong tree stops quickly because the tree and the car body together supply a force large enough in a short time to change the car's momentum. Move a sofa that has sat for years and you meet two partners at once, mass and friction. Mass resists acceleration. Friction resists sliding. The same rule holds in space. Planets, stars, and galaxies move because they were set into motion, and because space offers little to slow them. Planets follow paths set by gravity and their initial velocities. Stars orbit in galaxies. Gas clouds drift and collide. None of this requires continuous pushing. It requires the forces that are present, gravity, pressure, magnetic fields, to set or change motion. When forces are small or balanced, motion continues as it was. When forces add up, motion changes. Stopping a moving object takes as much care as starting it. A train and a tricycle show the contrast. The train's mass is huge, so for the same braking force it takes much longer to reduce its velocity. The tricycle's small mass means much less momentum at the same speed, and a small force can stop it quickly. The principle is the same, only the numbers differ. Underneath the examples is one idea: matter resists change. This is not a mood or a choice, it is the way mass and motion work. Atoms, molecules, rocks, and gases all follow the same rule. That consistency is useful because it makes the world predictable. Push, and the object responds in a way you can measure and model. Do not push, and it keeps its state. Balance makes this clearer. A person standing still is not motionless because time has paused. Gravity pulls down. The ground pushes up with an equal normal force. Horizontal forces are small or cancel. With no net force, the velocity is zero and stays zero. If something unbalances the forces, a gust, a shove, a trip over a step, the state changes. Inertia does not favor either outcome. It only resists the switch from one to the other. This neutrality invites a careful way to read cause and effect. If an object speeds up, slows down, or turns, something acted. The goal is to identify that something and measure it. Often, the something is friction. Friction does not draw much attention, but it shapes nearly every motion we see. Without friction, walking would be sliding, braking would be hard, and tools would be difficult to hold. With friction, shoes grip floors, tires grip roads, and pens grip paper. Friction is not dramatic, but it is reliable. In the language of forces, friction opposes motion between surfaces in contact. There are two common types. Static friction acts when surfaces are at rest relative to each other. It adjusts up to a maximum value to prevent sliding. This is why your foot does not slip each time it lands. Static friction between sole and ground supplies exactly the force needed to keep your foot from sliding, up to a limit set by materials and load. Once sliding starts, kinetic friction takes over. Kinetic friction resists sliding at a roughly steady level, usually lower than the peak static value. That difference explains why starting a heavy box moving is harder than keeping it moving once it slips. Air resistance, or drag, plays a similar role for objects moving through air. Drag pushes back opposite the motion. At low speeds it is small, but it grows as speed increases, often with the square of speed for bluff objects. This is why cyclists feel a strong push of air at high speed, and why modern cars are shaped to let air flow smoothly around them. A skydiver falls faster and faster until drag grows enough to balance weight. At that point, the net force is zero, and the speed becomes constant. That steady speed is terminal velocity. Change body position, and the drag changes, shifting the terminal speed up or down. Remove air and friction, and the first law shows its pure form again. In vacuum, a push sets a new velocity that persists until a force acts later. This is the context for spaceflight. In orbit, low drag means long coasting with only small corrections. Outside the atmosphere, probes travel between planets on paths set by short engine burns and long stretches of inertia guided by gravity. What causes friction at the microscopic level is not a special field or hidden particle. Surfaces that look smooth or rough under magnification. Tiny peaks and valleys touch and interlock. When a block moves, these rough spots bend and break. Energy turns into heat. Molecules also attract each other at contact points. This adhesion adds to friction. The more contact area under pressure, the more chances for those tiny junctions to form. The result is resistance to sliding. The details vary with materials. Clean metal on metal can show high friction because of adhesion. Lubricated surfaces can show low friction because a thin fluid layer separates the solids and shears more easily than solids rubbing. Friction allows control during turns. When a car rounds a curve, the tires push sideways on the road, and the road pushes back with static friction. That sideways friction provides the inward force that changes the car's direction. If tires lose grip on ice, the friction falls and the car tends to continue straight. The driver can turn the wheel, but with little friction, the needed sideways force is missing. In that moment, the first law is visible. The car keeps its velocity until a force changes it. Sometimes we want high friction. Shoes, tires, handrails, and climbing holds all rely on friction to prevent slipping. Sometimes we want low friction. Skates and skis use low-friction contact to glide. Bearings use smooth rolling elements and lubrication to reduce resistance. Oils and greases keep metal surfaces apart and carry away heat. Graphite and certain ceramics can slide with low friction due to their layered structures. Engineers tune surfaces and lubricants to hit the right balance. Enough grip to control, low enough resistance to limit wear, and wasted energy. Everyday tasks make the trade-offs clear. Dragging a couch across carpet feels difficult because the heavy load increases the normal force and the fibers deform, creating many contact points that resist motion. Lighter objects press less and are easier to move. Replace carpet with a slick floor and sliding becomes easier because fewer fibers engage and the contact is simpler. Add sliders or rollers and resistance drops further. None of this changes the law. It just changes the forces at work. Friction also causes wear. The same microscopic contacts that resist sliding break and tear material. Soles thin, hinges loosen, gears lose material on their teeth. Wind-blown sand smooths stones over long times. Engineers fight wear with better materials, hardened surfaces, careful shapes, and lubricants. They also accept that some loss is inevitable and design parts to be replaced when needed. Not all friction is about sliding solids. Fluids rubbing on solids and on themselves create viscous friction. Stirring thick syrup takes more effort than stirring water because the internal friction in syrup is higher. We describe that with viscosity. Air flowing around a bluff object separates and forms swirls that add form drag, while air smoothly following a streamlined shape creates less resistance. Designers use these ideas to reduce power needs, cut noise, and improve control. Sound links to friction in a simple way. Rubbing surfaces makes vibrations. Vibrations travel as waves in air and reach your ear as sound. Musical instruments use controlled friction and resonance to produce tones. A bow drawn across a string sticks and slips in a regular pattern, feeding energy into the string's vibration. Chalk squeals because tiny stick-slip motions excite frequencies that your ear finds sharp. The same basic process, friction turning organized motion into heat and vibrations, runs through many devices. Material and surface choice matters. The coefficient of friction is a number that compares frictional force to the normal force pressing surfaces together. Ice has a low coefficient, which is why sliding is easy. Rubber on dry asphalt has a high coefficient, which is why tires grip. The actual value depends on details: surface finish, temperature, contamination, and speed. Engineers measure these coefficients and use them to predict required forces, stopping distances, and wear rates. The presence of friction can mislead our intuition about inertia. Throw a ball and watch it slow on grass. It is tempting to say motion fades on its own. The better reading is that grass applies a force opposite the motion, and air adds drag, so the net force is not zero. The first law still holds. Where forces are balanced or absent, velocity is steady. Where forces act, velocity changes. Keep this frame, and many scattered facts line up. The same frame helps read balance problems. A book resting on a level shelf stays at rest because the net force is zero. Gravity pulls down. The shelf pushes up with an equal normal force. If the shelf tilts, a component of gravity acts along the surface, and the book slides if static friction is not strong enough to hold. If the friction limit is higher than the downslope pull, the book stays. The numbers decide the outcome, not a built-in preference for rest or motion. Even in high-speed systems, the principles remain. A racing car uses downforce from its wings to increase the normal force and thus increase the available friction, allowing tighter turns without sliding. A high-speed train reduces rolling resistance with smooth profiles and uses steel-on-steel contact, which has modest friction. Control comes from large contact area and precise suspension. In laboratories, air tables and magnetic levitation reduce friction so that small forces and clean motions can be measured and tested. Deep space shows the extreme case again, with almost no molecules to provide drag and no surfaces to rub. A gentle push leads to long, steady motion. Planetary gravity fields curve paths and form orbits. Small thruster firings trim routes. Mission plans are built around these facts. Short thrusts, long coasts, and precise accounting of small forces like sunlight pressure. Friction is the quiet equalizer of motion. It is always present, balancing movement with gentle resistance. Socks cling to carpet, brakes squeak. A pen hesitates on rough paper, not because anything is offended, but because friction is doing its job, slowing motion, smoothing edges, and keeping objects from sliding away. Mass sits close to this story. We use the word often, but in physics, it has a specific meaning. Mass measures inertia, the resistance to changes in motion. Weight is the pull of gravity on mass and changes from place to place. Mass itself does not. On the moon, you would weigh less because gravity is weaker, but your mass and your resistance to acceleration would be the same. Put a bowling ball and a tennis ball on any world. The bowling ball has more mass, so it resists being sped up or slowed down more strongly. A shopping cart shows the idea in simple form. Empty, it responds to a light push. Packed with cans and a melon, it takes more force to start and more force to stop. The top speed you could reach is not defined by mass alone. What changes is how hard you must push to change the cart's speed. Newton's second law summarizes this. Force equals mass times acceleration. For the same force, a larger mass means a smaller change in velocity per second. That is why a parked car does not move just because you want it to, and why a train takes a long stretch of track to slow, even when brakes press hard. By contrast, a fly in mid-air has very little mass and very little momentum, so a screen or a breeze can stop it quickly. Momentum is closely tied to mass. It is the product of mass and velocity. Double the mass while keeping speed the same, and momentum doubles. Double the speed with the same mass, and momentum doubles again. Momentum is a measure of how difficult it is to change motion. A cannonball and a ping-pong ball, moving at the same speed, carry very different momenta. One is easy to stop, the other is not. Steering works the same way. Heavy trucks and large ships need more time and distance to turn because their momentum resists quick changes in direction. In space, the effects are clear. With very little drag, a satellite keeps its path once set. To change that path, thrusters must supply a force for a certain time, and the result depends on the spacecraft's mass and current velocity. Even small adjustments are planned with care because every change in speed, however small, requires a precise push. Mass is also a basic property of matter at the smallest scale. Atoms have mass because their particles, protons, neutrons, and electrons have mass. Modern physics explains part of this through the Higgs field, a field present everywhere that interacts with particles. The stronger the interaction, the greater the particle's inertial mass. The discovery of the Higgs boson confirmed the mechanism, though everyday inertia still feels simple. More mass, more resistance to change. Daily life keeps returning to the same principles. Opening a heavy door takes more force than opening a light one. Throwing a snowball is easier than throwing a frozen turkey because the larger mass resists the same acceleration. When a bus accelerates, your body leans because your mass resists the change in velocity until the seat and floor provide the needed forces. Even at rest, mass matters. Sitting on a chair, your weight presses down. The chair provides an upward, normal force of equal size. The balance of forces keeps you still. Without mass, there would be no inertia to resist change. Without that resistance, motion and contact would not be controllable. The resistance that comes with mass is often practical. It prevents objects from jumping at small disturbances. Shelves do not topple from a light breeze because the forces are too small to overcome friction and inertia. It also means meaningful movement costs energy. Machines, vehicles, and rockets must supply forces to change states of motion, and that cost is predictable, which allows design and planning. Seeing mass as inertia clarifies many comparisons. A parked car and a falling apple obey the same rules. So do a puck on ice and a spiral of stars in a galaxy, once the relevant forces are counted. To be heavier, in the colloquial sense, is to resist changes more. The object pushes back. Only in the mechanical sense, its mass demands a larger force to achieve the same acceleration. A familiar scene shows these rules at work with fluids. Carry a cup of coffee. You and the cup move together. The liquid inside also moves, but it behaves differently from a solid because it can flow. When you start walking, the coffee lags. When you stop, it keeps going. Each step adds a small acceleration to the cup, and the liquid responds with waves that travel across the surface, reflect from the cup's walls, and interact. This is sloshing dynamics. If the timing of your steps matches the natural slosh frequency, the wave grows by resonance and can crest over the rim. Small changes reduce the effect. Holding the cup closer to your body lowers the pendulum-like swing of your arm. Walking a little slower shifts the timing so your steps do not pump the wave at its natural rhythm. Bending your elbow and letting the cup move slightly in your hand can absorb jolts before they reach the liquid. These intuitive habits break the synchronization and cut spill risk. Engineers use the same ideas at larger scales. Baffles inside fuel tanks disrupt slosh. Guidance systems time maneuvers to avoid exciting fluid motion. The same inertia that drives slosh also acts on your arm and the cup. When you halt suddenly, your torso stops first. Your arm swings forward. The cup follows, and the coffee continues until the wall of the cup provides the force to redirect it. In a car, a sudden brake does the same to everything inside. Cups, bags, and passengers move forward until seat belts, dashboards, or seats apply forces to change their motion. The first law is visible whenever a stop or turn is sharp enough to be felt. Friction returns here as a partner to inertia. The coffee's surface interacts with the cup. Small viscous forces inside the liquid dissipate energy and eventually calm the waves if new jolts stop arriving. Air above the coffee adds light drag. On the road, tire friction with the pavement provides the needed sideways force for a turn. If that grip drops on ice, the car tends to continue straight, even if the wheel is turned. Static friction supplies the force while rolling without slipping. Once grip is lost, kinetic friction is lower, and control is reduced. Materials and surfaces control how much friction is available. The coefficient of friction summarizes how grippy a pair of surfaces is. Rubber on dry asphalt has a high coefficient, allowing strong braking and tight turns. Ice has a low coefficient, making sliding easy and stopping hard. Lubricants reduce contact between solid peaks, turning solid-solid friction into fluid shear, which can be much lower. In machines, bearings, and oils limit energy loss and wear. In sports, smooth ice and sharp blades reduce resistance and allow long glides. Wear is the long-term companion of friction. Microscopic contacts break and reform, slowly removing material. Soles thin, hinges loosen, gear teeth polish. Designers select harder materials, coat surfaces, or add sacrificial layers to extend life. They also accept that parts will be replaced after a known service interval because the physics of contact does not pause. Air resistance adds another layer. At low speeds, drag may be small. At higher speeds, it grows rapidly, often with the square of speed for many shapes. Streamlined forms reduce separation and swirling, cutting the pressure drag. Cyclists lower their posture. Vehicles use smooth contours. Aircraft and rockets manage airflow with precise geometry. In freefall, drag grows until it balances weight, setting a terminal velocity. A parachute increases area and drag, lowering that terminal speed to a safe value. These pieces fit back into the same framework. Inertia preserves the current state. Mass measures how hard it is to change. Momentum accounts for motion that must be redirected. Forces friction, drag, gravity, tension, normal forces, thrust, explain every change. Balance them, and motion is steady. Unbalance them, and motion evolves in specific, measurable ways. Seen this way, socks on carpet, trains braking, a pen on paper, a loaded cart in a store aisle, a satellite coasting in orbit, and a cup of coffee on a busy morning all share the same set of rules. A sip in a moving car can turn into a spill for the same reason. The liquid keeps its motion while the cup, your hand, and the car change theirs. It helps to think about the center of mass, the average location of the liquid's mass at any moment. In a solid, that point moves with the object. In a cup of coffee, it shifts as the surface tilts and waves travel. If the liquid surges forward and up at the rim, the edge no longer blocks it, and the coffee escapes. The effect depends on speed, step timing, and how steady the hand is. The physics is simple in idea and surprisingly rich in detail. Robotics brings this down to code. Teaching a robot to carry soup without spilling means modeling slosh, anticipating accelerations, and choosing a grip and path that dampen waves. A human adjusts without thinking, elbow bends, wrist angles, a shorter stride. A robot must measure, predict, and plan. Avoiding a spill is not clumsiness versus skill. It is control of a dynamic system. Every step with a cup is a small experiment. Acceleration from your stride sends a wave. The wave reflects from the wall. Two waves add and make a larger crest, or cancel and flatten. If your step rate matches the cup's natural slosh frequency, resonance builds the wave until it spills. Change the step rate, hold the cup closer to your body, or let your wrist move to absorb jolts, and the resonance breaks. The same idea shows up on airplanes. A sudden bump changes the cabin's motion, but the drink keeps its earlier velocity until the cup redirects it, which can be too late to prevent a splash. Inertia gives motion a kind of memory, not a mind, just a rule. Velocity stays the same unless a force changes it. The redirection is not always gentle. It happens through splashes and impacts that remind us that forces do the changing and timing matters. The consistency is the lesson. The rules that shape satellites and asteroids also shape a morning beverage. A step, a pause, a small spill, all follow the same law. Vehicles show the rule at larger scale. Riding at highway speed, everything in the car shares the same velocity. The passengers, the seats, the cup in the holder, even the loose coins in the tray. When the car slows smoothly, forces act over time, and everything slows together. When the stop is sudden, inertia shows itself. The car decelerates, but loose objects and unrestrained bodies continue forward until another force stops them. Safety design accepts this and works with it. Seatbelts tie the person to the vehicle's frame at strong parts of the body, the pelvis, and chest. In a rapid stop, the belt applies a distributed force and stretches slightly so the deceleration happens over a longer time. Spreading the stopping over tens of milliseconds instead of a few makes a large difference in peak force. Airbags add another step. Sensors detect a crash and trigger inflators that fill a bag in a few hundredths of a second. The bag provides a larger, softer surface that increases stopping time again. The goal is simple: reduce peak forces by extending the time over which momentum changes. Crumple zones do similar work with structure. The front and rear of a car are designed to deform in a controlled sequence. Metal folds and absorbs kinetic energy so that less reaches the passenger compartment. A rigid shell from bumper to bumper would transmit more force to the occupants. By allowing parts to collapse in a planned way, the structure turns energy into deformation. Laminated windshields join the strategy. 2 glass layers and a plastic interlayer keep fragments bonded when the glass cracks, avoiding sharp shards. Side beams, head restraints, and energy-absorbing columns continue the same theme: redirect forces around people and lengthen the time of deceleration. Sensors tighten belts and position headrests even before full impact if a collision is imminent. Each feature is an answer to the same questions: how much momentum must change, where will the energy go, and how can the forces be managed so the body experiences less peak load. Mass is part of the calculation. A heavier vehicle carries more momentum at the same speed, so more energy must be absorbed in a crash. Weight distribution matters too. Engineers route loads into paths that bypass the cabin and test the behavior in computer models before building prototypes. Crash test dummies with sensors provide data on accelerations and forces to refine designs. Each test is a study in managing inertia rather than denying it. The same acceptance appears in flight. A rocket climbs on thrust to gain speed and altitude. Once outside most of the atmosphere, engines can shut down and the vehicle keeps going. Space is nearly free of drag, so motion continues until gravity, thrusters, or a collision changes it. A spacecraft in low Earth orbit needs occasional reboosts because a thin trace of atmosphere still causes drag. Higher up, even that small effect fades and orbits persist longer. Transfers between orbits use short burns timed at precise points so that a small change in velocity produces a large change in path over time. The plan is bursts of force followed by long coasts. The contrast with Earth is the point. On the ground, friction and air resistance are constant partners. Tires grip because static friction supplies the sideways force needed to steer and brake. If grip drops on ice, the car tends to continue straight, even with the wheel turned. In air, drag grows with speed, which is why streamlining matters and why high speeds require much more power. In water, Viscous forces and added mass affect maneuvering, so ships and submarines respond slowly. Each medium adds forces that push motion away from the ideal of steady velocity. Back to liquids. The center of mass helps predict behavior during turns and stops. If the combined center of mass of the cup and liquid swings outside the base of support, the cup tips. Keeping the cup lower and closer to the torso reduces lever effects and keeps the center of mass over the feet during walking. The same idea helps robots. A robot that models the combined center of mass and anticipates slosh can adjust foot placement and wrist motion to keep the system stable. Designers use small structures inside tanks' baffles to break up wave motion. Baffles reflect and absorb slosh, so waves cannot grow with each jolt. Spacecraft, rockets, and even trucks that carry liquids rely on baffles to keep loads stable. Fuel in a large tank can shift and move the center of mass, changing control forces. Reducing that motion improves steering and guidance. The technique echoes what a person does with a wrist: interrupt the rhythm so waves do not add. Inertia also frames why stopping distances scale as they do. The work needed to remove kinetic energy grows with the square of speed. Double the speed, and the energy is 4 times larger. Brakes must convert that energy to heat. Tires must hold the road without sliding. Road surface, tire condition, and temperature set the limits. Anti-lock braking systems pulse pressure to keep tires near the peak of friction, allowing steering while braking. Again, the pattern is the same. Use available friction well, avoid lockup, and manage forces over time. Aircraft cabins give another view. During turbulence, a sudden vertical acceleration changes the plane's motion, but drinks and loose items follow their previous paths for a moment. Seat belts do for vertical jolts what car belts do for forward stops. Apply forces over time to keep passengers attached to the moving frame. Overhead bins latch to keep masses from becoming projectiles. The rules do not change with altitude. Only the typical directions and magnitudes of forces change. At the level of a single person walking, the body constantly balances forces. The foot on the ground experiences static friction that prevents slipping while the other leg swings. The center of mass moves forward over the base of support, and small muscle forces steer it back if it drifts. Carrying a full cup changes the rhythm. Many people slow their step, shorten their stride, and relax the elbow to add a small suspension between body and cup. Each adjustment reduces the sudden accelerations that feed slosh. A simple formula connects these outcomes. Force equals mass times acceleration. For a given maximum force set by friction at the tires, the strength of a belt, or the grip of a hand, the allowable acceleration is limited. To stay within limits, spread the change over more time. Reduce mass, where practical, or reduce speed. Safety systems apply all three. They stretch time, shape structures to route forces, and encourage speeds that match conditions. Even materials are chosen with these ideas in mind. Seat belt webbing must be strong, yet stretch slightly under high load. Airbag fabrics must allow gas to vent in a controlled way so pressure drops as the person contacts the bag. Metals in crumple zones must deform predictably rather than snap. Glass interlayers must hold fragments. Each choice supports the same target control. The way motion changes. Space missions use a quiet version of the same thinking. Solar radiation pressure can add tiny forces to a spacecraft over long times. Operators plan small burns to counter these drifts. Thruster firings are short and precise because every change in velocity adds up. The absence of friction does not mean an absence of planning. It means planning focuses on gravity, radiation pressure, and the geometry of orbits. The unifying view is straightforward. The liquid that sloshes, the body that leans in a stop, the belt that stretches, the airbag that inflates, the metal that crumples, the rocket that coasts, and the satellite that circles all follow the same set of laws. Inertia keeps a state until a force acts. Mass measures how hard that state is to change. Momentum captures motion that must be redirected. Friction, drag, gravity, and engineered restraints provide the forces that produce the changes. When those forces are managed with timing and design, motion changes in controlled ways rather than sudden ones. The engines give a spacecraft its initial push. They supply the force needed to climb out of thick air, overcome gravity near the surface, and build speed. Once above most of the atmosphere, resistance is small, so the craft can coast. In space, you do not burn fuel to keep moving. You burn fuel to change how you are moving. Short bursts change speed or direction. Without a planned change, velocity stays as it is. This is also why people appear to float aboard the International Space Station. Gravity has not vanished there. It is only a little weaker than at Earth's surface. The station and everything inside it are in continuous freefall. The vehicle moves forward fast enough that as gravity bends its path downward, Earth's surface curves away at the same rate. The result is an orbit. The station circles the planet roughly every 90 minutes, crossing day and night many times in one Earth day. Astronauts float because they, the station, and the objects around them fall together at the same rate, with no floor pushing up on them to create the sensation of weight. In this balance, inertia and gravity work together. Inertia keeps the station moving straight. Gravity pulls inward. The combined result is a curved path that neither flies off nor plunges down. When the mission ends, the craft cannot turn off motion. Engineers aim the vehicle backward and fire retro rockets to reduce speed. A small drop in orbital velocity lowers the path into denser air. Drag then does steady work, converting kinetic energy to heat. The heat shield glows, the craft slows, and parachutes or engines finish the job. The change from steady orbit to landing is a planned sequence of forces acting over time. Steering in space follows the same laws without a road to push against. Spacecraft use reaction control thrusters placed around the hull. A short puff of gas in one direction produces rotation the other way. Newton's third law explains the effect. Action and reaction are equal and opposite. Once the vehicle is spinning, it keeps spinning until another torque cancels it. Astronauts feel this directly. Twist a wrench without bracing feet or hands, and both astronaut and tool rotate in opposite directions. Handrails and foot restraints provide anchors so that applied forces do not send the person drifting. Loose tools illustrate inertia in microgravity. A screwdriver released from a hand does not stop near where it was let go. It keeps its small velocity until it touches a wall or is caught. Because there is no floor friction to halt it, careful habits and tethers keep objects from roaming. Organization in the cabin is not only tidy practice, it is physics management. Simple demonstrations make these rules easy to see. Drops of water cling to surfaces by surface tension and drift quietly in the cabin. A spinning disk with a water drop on it shows both translation and rotation without gravity settling the drop. Motions are clean because air currents are weak and contact forces are controlled. Space removes many disturbances, so Newton's laws show through with less noise. The same logic scales up to planets and comets. Earth orbits the Sun because it moves forward fast enough that the Sun's gravity bends, rather than ends, its path. The Moon orbits Earth for the same reason. Comets trace elongated paths set by their initial speeds and the pull of the Sunday. Nothing holds these bodies up. They are always falling and always moving forward, so the fall curves into a loop. The rule is simple. With no net external force, an object keeps its velocity. With gravity present, the velocity changes in direction in a predictable way. A basic picture called Newton's cannon helps fix the idea. Imagine launching a ball horizontally from high altitude. At a low speed, it lands nearby. At a higher speed, it lands farther away. At a particular speed, about 7.8 kilometers per second, near low Earth orbit, it falls toward Earth, but Earth curves away beneath it at the same rate. The ball never reaches the ground. It falls around the planet. This speed is the orbital velocity for that height. Closer orbits require higher speeds because gravity is stronger. Higher orbits need less speed. Geostationary orbits sit much farther out. There, a satellite circles once per day, matching Earth's rotation so it appears fixed in the sky to a ground observer. Weather and communication satellites use this position to watch the same region continuously. Reaching such an orbit requires both the right altitude and the right speed. Going beyond Earth entirely requires a different target: escape velocity. Near the surface, an object leaving in a straight shot without further pushes must reach about 11.2 kilometers per second to break free. Missions normally do not jump straight to that speed at the surface. They build speed in steps and use orbits and timed burns to reach interplanetary paths efficiently. Orbits are not all circles. Ellipses are common. The object moves faster when closer to the body it orbits and slower when farther away. Comets spend most of their time far from the Sun, moving slowly, and then sweep quickly through the inner solar system. The same rules apply at every point of the path. Momentum carries the object forward. Gravity changes the direction. The result is a smooth cycle defined by initial conditions and the masses involved. Weightlessness in orbit is often misunderstood. Gravity is strong enough to keep the space station and the astronauts circling Earth. What has changed is the presence of a supporting surface. On the ground, the floor pushes up on your feet, giving the sensation of weight. In orbit, no surface continuously pushes up, so the body feels weightless. Instruments still register gravity as they track the curve of the path. Experiments still must account for small residual accelerations, airflows, and vibrations from equipment, but the dominant feeling is free fall. Maneuvering around a station or a satellite involves both translation and rotation. To shift position without bumping into things, small jets provide gentle pulses. Once moving, the astronaut or vehicle will keep that motion until an equal and opposite change is applied. Orientation control uses gyroscopes and reaction wheels as well as thrusters. Spinning up a reaction wheel rotates the spacecraft in the opposite direction. Spinning it down reverses the effect. These systems conserve angular momentum within the closed system of spacecraft plus wheel, allowing fine pointing for cameras and antennas. On the return to Earth, the physics reverses. A precise change in velocity targets the entry corridor. Too shallow, and the craft may skip through the upper atmosphere. Too steep, and heating and forces rise to unsafe levels. The thermal protection system handles the heat load by re-radiating and carrying energy away as gases ablate. The craft's shape generates lift, giving control over the path through thin air. As speed drops, thicker air increases drag, and parachutes, wings, or landing rockets handle the final phase. Every step is timed so that forces act within known limits. Even stable orbits change slowly. At low altitudes, thin air causes drag. The International Space Station uses reboost burns to counter this and maintain altitude. Farther out, tugs from the sun and moon, the slight unevenness of Earth's gravity, and solar radiation pressure all shift paths over time. Engineers plan station-keeping maneuvers to correct these drifts. In the Earth-Moon system, tides transfer energy from Earth's rotation to the Moon's orbit, causing the Moon to recede a few centimeters per year. Over long spans, these small effects matter. Placing satellites uses the same principles with different targets. Weather monitoring often needs geostationary orbits to watch continents. Earth mapping often prefers near-polar, low orbits that pass over each point at the same local solar time, called sun-synchronous orbits. Global navigation systems use medium Earth orbits to balance coverage and signal strength. Each choice sets a required speed and altitude. Small engines and, in some designs, electric thrusters make the fine adjustments needed to reach and hold the chosen path. On a spacecraft, fuel is precious because every kilogram launched costs energy. Mission plans therefore combine short thrusts with long coasts. Gravity assists add efficiency. A probe passing a planet can gain or lose speed relative to the Sun by exchanging momentum with the planet. The planet's path changes by an immeasurably small amount. The probe's path changes by a useful amount. This is not a push from the planet's air or surface. It is the result of moving through a changing gravitational field on a planned trajectory. Inside orbiting laboratories, fluid experiments take advantage of low effective weight. Liquids form spheres under surface tension without a strong gravity field to flatten them. Flames burn in round shapes controlled by diffusion rather than rising convection. Vibrations from equipment and crew motion still introduce small accelerations, so experiments use isolators to reduce these jitters. The cleaner environment reveals processes that air, currents, and buoyancy hide on Earth. The same balance that keeps satellites in place guides re-entry debris and meteors. Small objects without control or heat shields ablate and break apart, high in the atmosphere. Larger objects need careful planning at end of life, so fragments land in remote ocean areas. Understanding drag, heating, and breakup allows safe disposal. At the other end of the scale, natural bodies like meteoroids release light and sound when they deposit energy in air, and larger asteroids require tracking, so that rare but important impact risks are known. The equations behind these behaviors are compact. Acceleration equals force divided by mass. Gravitational acceleration near Earth decreases with altitude, but remains strong in low orbit. Orbital speed depends on distance from the center of the planet. Energy changes with speed squared. In practice, the simplicity helps. With a few well-measured numbers, mass, altitude, speed, engineers can model paths before a vehicle ever leaves the pad, then adjust with small burns once in flight. Comparisons with motion on Earth highlight the differences and the continuity. Turning a car requires lateral tire forces from friction. In orbit, turning requires a sideways push from thrusters or a gravity field. Maintaining highway speed in air takes steady engine power to defeat drag. Maintaining orbital motion requires no power at all, only occasional corrections. Stopping on a road converts kinetic energy to heat in brakes and tires. Stopping from orbit converts much larger energy to heat in air and heat shields. In both cases, the aim is to manage forces so that changes happen within the limits of materials and the human body. Orbital mechanics also explains familiar satellites in the sky. The International Space Station moves quickly across the evening, bright for a few minutes as it reflects sunlight, then fades as it enters Earth's shadow. A geostationary satellite stays fixed above the equator, as seen from one location. Small station-keeping maneuvers keep it in its assigned slot. A GPS satellite completes 2 orbits per sidereal day at medium altitude, sending timing signals that receivers use to measure distance. Each roll chooses an altitude and speed that fit the task. None of this requires special pleading or separate rules for different places. The same laws link a cup that drifts in a cabin to a planet that circles a star. Start with mass and velocity. Identify the forces. Sum them to find the net. Predict the change. In space, the list of forces is short, mainly gravity, small thrusts, sunlight, and occasional dust. On Earth, the list is long gravity, normal forces, friction, drag, buoyancy, and more. The method does not change, only the terms in the sum. This is why a rocket can cut its engines and keep going, why an astronaut floats while working, why a satellite remains above the same point on Earth, why a craft needs only brief firings to shift its path, and why a controlled return requires careful timing and heat protection. It is the same framework that explains why low orbits decay, why the moon drifts away slowly, why comets speed up near the sun and slow in the outer dark, and why a small correction far from Earth can place a probe on a precise path weeks later. Step outside on a clear night and the sky looks calm. The light points seem fixed, the arcs are slow, and nothing appears rushed. Yet every dot is moving under the same rules. Inertia does quiet work here. It keeps the motion steady, unless a force steps in. Gravity is that constant force, always pulling, always redirecting, but rarely stopping things outright. The result is not random drift, it is orderly paths that persist for long times. Moons are a simple place to start. Earth's moon is not hanging in place. It is moving forward while gravity bends its path inward, so the fall curves into an orbit. The path is slightly elliptical, not a perfect circle, but the idea holds. Forward motion plus gravitational pull gives a loop that repeats. Jupiter's major moons Io, Europa, Ganymede, and Callisto show the same rule with added structure. Their periods are locked in resonances. For example, Io, Europa, Ganymede in a 1, 2, 4 pattern, so their positions repeat in a stable rhythm. They are not spiraling in because their inertia balances the pull. Over longer spans, small exchanges of energy can shift orbits, yet on human timescales, the paths are steady. Tides bring slow change. The gravity between a planet and a moon raises bulges that lag a bit due to friction inside the bodies. Energy moves between spin and orbit. In some systems, the orbit grows. In others, it shrinks. Mars's moon Phobos is losing altitude by a few centimeters per year and will break up or fall far in the future. Earth's moon is drifting away by a few centimeters per year as Earth's rotation slows. These rates are small, but across millions of years they add up. Even so, on the scale of nights and lifetimes, inertia and gravity produce orbits that look fixed and calm. Between Mars and Jupiter lies the asteroid belt. It holds a wide range of bodies, from dwarf planet Ceres to boulders and dust. Each asteroid follows the same forward-falling path around the Sunday. Some orbits are nearly circular, others are stretched out. Jupiter's gravity shaped this region. Its strong tugs prevented a single planet from forming and cleared regions called Kirkwood gaps, where orbital periods would match simple fractions of Jupiter's period. Once asteroids settle into stable paths outside those gaps, they need no push to keep going. Their inertia carries them. Gravity guides them. Comets trace larger and colder routes. Many come from the Kuiper belt beyond Neptune. Others come from the distant Oort cloud. A small nudge from passing stars or the combined pull of the galaxy can change a comet's path and send it inward. As a comet warms near the sun, ices vaporize and release gas and dust, forming a coma and tails. One tail points roughly away from the sun due to the solar wind. A dust tail curves under the comet's path due to sunlight pressure and the particle's inertia. Near the sun, the comet speeds up. Far away, it slows down. The same rules that govern satellites and moons govern these long loops. Unless a force changes the path, say a close pass by a planet, the comet will return again. Meteoroids are small fragments moving on their own solar orbits. When one intersects Earth's path at the same time Earth is there, it enters the atmosphere at high speed. Air compresses in front of it and heats, generating the light of a meteor. Most burn up. A few reach the ground as meteorites. None of this is random in the physics sense. The paths are set by initial speeds and directions plus gravity. A chance impact is an accurate alignment in time and space. Two paths cross at one point at one moment. The same logic explains outcomes of impacts. Speed, direction, and mass decide how energy is delivered and where fragments go. Slow, shallow encounters can lead to capture if energy is dissipated. Fast, steep ones shatter or excavate craters and launch debris into new orbits. The billiards picture is not perfect, but it is close. Add vectors, count energy, expect inertia to carry fragments along new lines until forces act again. Voyager 1 and Voyager 2 show inertia on a human-made scale. Launched in the late 1970 seconds, they used a series of gravity assists to gain speed and aim toward the outer solar system. Their main engines have long been silent. Each craft continues outward on a path set by those early maneuvers, with only small course corrections during the planetary tours. The radio signals are faint but measurable. The motion needs no further push. It persists in the quiet space between stars. The wider universe follows the same script. Stars orbit the centers of galaxies. Galaxies move within clusters. Clusters shift within larger structures. These motions add vector upon vector, but they do not erase the core rule. Inertia keeps states. Gravity curves paths. Where forces are small, motion changes slowly. Where forces are strong, paths bend quickly. It is a continuous system, not a set of special cases. Falling sounds like a path to a stop. In space, falling can be continuous because there is no surface to end the path. Moons fall around planets. Planets fall around stars. Stars move in the mass field of the galaxy. The word weightless in orbit means there is no support force acting on the body, not that gravity is missing. Inertia makes the forward motion last. Gravity supplies the steady inward change in direction. When a force finally appears, air drag on re-entry or a collision, the state changes. The idea of inertia also appears outside mechanics in a careful, analogous way. In biology, systems often resist change unless a strong pressure acts. Evolution is the long record of change. but it also shows long spans of stability when traits work well enough in the current environment. Evolutionary inertia is not a force, it is a description of how inherited structures and successful strategies persist. Some lineages have kept similar forms for very long times because their designs fit their roles. Sharks, crocodiles, and horseshoe crabs are well-known examples. Their environments and ways of life have not demanded radical redesigns. So natural selection has kept their shapes close to already successful patterns. Change still occurs, but within bounds that keep function intact. Constraints shape what is possible. Mammals share a strong pattern in the neck. 7 cervical vertebrae in almost all species. Giraffes do not add more bones. They elongate the same 7 segments. Changing the count would require deep changes in early development, which tend to have many side effects. Because the existing pattern works across many niches, selection tends to conserve it. The same pattern appears in limbs. The basic plan: 1 long bone, 2 next bones, small wrist or ankle bones, and digits appears in arms, wings, and flippers. Wings in bats and flippers in whales are remodels of the same parts, not entirely new parts. At the molecular level, the genetic code is nearly universal. The mapping from 3 base codons to amino acids is shared from bacteria to mammals. This uniformity suggests that once a working code appeared early in life's history, switching to a different code would break the protein-building machinery. To change it globally would require coordinated changes in many components, which is unlikely to succeed. The system persists because it works, and because partial changes would be harmful. Ecosystems also show stability through feedback. In a forest, grassland, or reef, populations and resources interact. Predators limit prey. Prey support predators. Plants and pollinators match each other's cycles. If a variable moves, others respond and tend to nudge the system back toward a range. This is dynamic stability, not a frozen state. It can be disrupted by strong pressures, such as climate change, habitat loss, invasive species, or disease. When a threshold is crossed, the system can shift to a new pattern that is hard to reverse. That difficulty is another form of persistence. After a collapse, the new arrangement can be stable against small pushes, just as the old one was. Traits can linger after their original roles fade. The human appendix is often cited as a remnant of a larger plant-digesting system in our ancestors. Goosebumps raise hair in mammals to trap heat or signal threat. With little body hair, the effect on humans is small. Wisdom teeth crowd, modern jaws that have changed with diet. These examples are not inert lumps. They are features that persist because selection against them has not been strong enough to remove them completely, or because they now have secondary roles. The pattern still reflects persistence. Once a trait is embedded in development, removing it can be costly, unless the benefits are large. The idea of path dependence in biology and society mirrors inertia. The current state depends on the past path taken. Small early choices or mutations constrain later options. This is not mystical. It is the practical result of building complex systems step by step. Life does not redesign from scratch each generation. It modifies existing parts. Changes that fit well accumulate. Changes that break, core functions are filtered out. Over time, lines of descent retain a recognizable backbone, with variations layered on. In cells, even basic regulation shows persistence. Networks of genes turn on and off with thresholds. Once a pattern is established during development, maintaining it requires only modest signals. Switching to a new pattern needs a larger, coordinated input. At the scale of bodies, habits in movement and metabolism reinforce stable states. In populations, behaviors and social structures can resist change until strong incentives or pressures act. These are not the same as mechanical inertia, but the logic of resistance to change appears in similar ways. In ecology, recovery can be asymmetric. Overgrazing can reduce plant cover, leading to erosion, which makes it hard for plants to return, even if grazing stops. The system has moved to a new state with its own stability. To move back, more than removal of the original pressure may be needed: soil rebuilding, reintroduction of key species, or changes in water flow. In that sense, inertia can work with a degraded state, holding it until significant work shifts it. Across scales, the practical lesson is consistent. Identify what keeps the current state in place. In mechanics, sum the forces. In evolution, examine constraints and selection pressures. In ecosystems, map feedback loops and thresholds. Changing a state requires the right kind of input, matched in size and timing to the resistance present. Without that input, the system keeps doing what it was doing. The night sky returns as the simplest reminder. The moon circles because its forward motion and gravity's pull line up to make a path. Jupiter's moons keep time in resonant steps. Asteroids coast along, guided by gaps and tugs. Comets sweep in and out along long ellipses. Meteoroids cross or miss. Spacecraft travel on planned arcs with brief bursts to adjust. None of these need continuous pushing. They need initial conditions, and sometimes small corrections. In living systems, persistence comes from success and constraint. Traits that work tend to stay. Body plans change slowly because they must keep working at every step. Genetic codes and core machinery hold because partial changes fail. Ecosystems stabilize through feedback until a strong nudge moves them. Even leftovers of past functions can remain when they do not harm enough to be removed. The theme is not stasis, it is steady continuation until a defined cause produces a defined change. Evolution keeps what works. It does not search for perfect designs. It keeps designs that are good enough to survive and reproduce. If a trait does not cause much harm, it may remain simply because replacing it would require many coordinated changes. Behaviors show this persistence too. Birds build nests in repeatable patterns. Wolves hunt in packs. Humans form bonds, share food, and care for young. These actions are shaped by selection across many generations. Once they fit into a way of life, they do not shift quickly. New pressures appear, but instincts do not vanish in a season. Change takes time, and living systems lean on what already works, while small adjustments gather. This persistence can be reassuring. Eyes, wings, fins, leaves. These forms look stable because they are stable. They adapt at the edges. If the environment stays steady, life leans on proven plans. When the environment changes, fast warming air and water, shifting seasons, new chemicals, evolution's usual pace can be too slow. The same stability that carried species through long ages can become a risk when conditions jump within decades. Many species now face pressures with no close match in their history. Fragmented habitats, light at night, city noise, novel diseases, rising heat waves. Even so, life shows responses. Some moths changed color to blend with urban soot. Urban birds adjust routes and timing as cities warm. Fish shift breeding windows as water temperatures move. These changes do not erase the slow nature of evolution, but they show that when pressure is strong and persistent, populations can track the change if enough variation exists. The river bends where forces are applied. It helps to remember that our bodies carry long histories. Bones, reflexes, and hormones come from older solutions that still work. A yawn, a stretch, a shiver, simple acts with deep roots. They remain because they helped past bodies cope with cold, effort, and low alertness. We move forward on the momentum of what came before. The past sets paths unless a stronger cause turns them. Daily life shows an echo of this in the mind. Routines are mental paths worn smooth by repetition. You wake, reach for the same cup, check the same screen, follow the same route. This is not failure, it is efficiency. The brain uses a lot of energy relative to its size, so it automates repeated tasks to save effort for new problems. Neurons that fire together strengthen connections. Over time, a set of steps, brush teeth, pack bag, lock door, runs with little thought. The benefit is speed and lower stress. The cost is that change takes a push. Starting a new habit often feels like moving a heavy object from rest. The first seconds are the hardest. Once it moves more easily. Stopping an old habit feels similar. Momentum keeps it going. Many plans fade, not because the plan is poor, but because the force needed at the start was not enough to overcome the mental static friction. A simple way to reduce that startup cost is to pair a new action with a stable anchor. Make a 2-minute stretch, follow morning coffee. Add a short walk after lunch. Put writing tools where you sit to read. Lowering the steps between intention and action reduces the needed push. Another quiet aid is to set very small first targets. Lace shoes, not run a mile. Open the file, not finish the report. These steps create motion. Once motion exists, it is easier to continue. Small progress produces small feedback, and the system tips toward the new path. Not every method works for every person, but the theme remains. Design the start to be light and clear, so momentum can build. Some resistances are social, not just personal. Belief systems and views also develop grooves. The brain prefers patterns that match what it already holds. New ideas that conflict feel like friction. Changing a view takes time because it involves building new links and weakening old ones. This is more than data. It is practice. Exposure, reflection, and conversations help shift the default lens through which new facts are read. The process is uneven and often slow, which is exactly why gentle, repeated inputs tend to work better than a single large shove. The same pattern scales up to groups. Institutions are bundles of rules, roles, records, and habits. A school, a court, a hospital network, each carries layers laid down over years. New layers must connect to old ones, or work will fall through gaps. Stability often ranks above speed, by design. That does not mean change is impossible. It means change must pass through checks that test clarity, cost, and side effects. During crises, those checks can feel too slow. In calmer times, they keep systems from swinging with each burst of opinion. Economic systems show similar dynamics. Money, contracts, supply routes, and standards form networks. A new policy can be sound and still take years to show full results because firms, workers, and logistics need time to adjust. Shocks spread with lags. A factory closure can ripple through suppliers and transport lines months later. A new technology can sit in pilot projects for years until training, parts, and customer habits align. This is not only about bureaucracy, it is about scale and interdependence. Standards and infrastructure create their own momentum. A keyboard layout, a gauge on a railway, a file format, a power socket, once widely adopted, they are hard to replace. The benefits of compatibility compete with the benefits of improvement. Switching costs include new equipment, training, and temporary loss of efficiency. The result is path dependence. The history of choices shapes future options. Energy systems are a clear case. Power plants, grids, mines, pipelines, and vehicles last for decades. Changing them is possible, but requires steady investment, planning, and time for old assets to retire and new ones to integrate. Network effects pull in the same direction. A communication platform or payment network becomes more useful as more people use it. Leaving is harder when contacts, records, and tools are tied in. Policies that support open standards or data portability can reduce lock-in by lowering the friction of moving, much like adding bearings to a heavy load. Legal systems also build inertia. Precedent guides decisions. Codes and regulations cross-reference each other. Updating one rule may require updates to dozens more. This web prevents sudden swings, but requires patience to revise. Public health systems face similar trade-offs. Protocols are tested and documented. Changing them requires evidence, training, and clear messaging. In emergencies, temporary measures allow speed, but long-term changes still pass through careful steps. Culture adds another stable layer. Norms, shared stories, and rituals guide behavior without written rules. They reduce uncertainty by telling people what to expect and how to act. Culture changes, but like language, it shifts through many small choices repeated over time. Migration, media, schools, and markets nudge the path, yet the change is usually gradual. This slow pace can frustrate, but it also keeps communities coherent during normal times. When rapid change is needed, the question becomes how to add enough force without breaking the system. In practice, this means aligning incentives, lowering barriers, and sequencing steps so each prepares the next. Pilot, learn, scale. Build capacity before deadlines arrive. Use clear rules that survive political cycles. Provide visible early wins to build momentum. These are not slogans. They are methods for adding directed inputs to a large, heavy system. Examples help. Switching to cleaner buses is slower if garages, parts, and mechanics are all set up for diesel. Planning ahead, training staff, stocking parts, updating software reduces friction when the first vehicles arrive. Shifting a hospital record system takes more than buying software. Workflows, privacy rules, and clinical habits must match. Breaking the project into phases lets staff gain comfort while problems are small. Education reform shows similar needs. Curriculum, assessments, teacher training, and support materials must line up. Changing one without the others produces drag. Aligning them reduces resistance. The timeline is measured in years because new students pass through grade levels and old materials phase out. The slow pace is not always a flaw. It can protect against fads. Markets add feedback. A price signal can shift behavior quickly if options exist. Without options, signals cause stress rather than change. Building options, public transit before congestion pricing, home insulation before energy pricing shifts makes responses smoother. In each case, the strategy mirrors physics. Reduce opposing forces, add steady inputs, and let momentum carry the system once it starts moving. At smaller scales, neighborhoods and firms use the same logic. A company that wants safer practices invests in training, clear checklists, and equipment that makes the safe choice the easy choice. Over time, the default path shifts. A city that wants more walking and cycling builds connected routes, calms traffic, and places services close to homes. Each small change adds to a new routine. After a while, the new pattern feels normal. These examples are not about wishful thinking. They show that large systems move with weight, and that weight can be guided. The guidance is most effective when it takes current paths seriously, acknowledging why they formed, what they support, and where they resist. Mapping those supports and resistances is like summing forces in mechanics. It shows where pushes help and where they only strain. Across biology, minds, and societies, the theme repeats. The present state persists when inputs are small or random. Change comes when inputs are clear, timed, and strong enough. In living systems, the inputs are selection pressures, development pathways, and resource flows. In minds, they are cues, rewards, and context. In institutions, they are rules, budgets, and shared expectations. The details differ, but the strategy of reading the current motion and shaping the next step is the same. The night sky remains a useful picture. Bodies trace paths set by starting speeds and steady pulls. Over long times, small forces, tides, faint drag, distant tugs shift those paths. The shifts are slow but real, and careful tracking makes them predictable. On Earth, we face something similar with systems we built. They carry momentum from past choices. They resist sudden turns. With enough resolve, clear plans, and steady application, the path bends. Without those, the path continues as it is. Large systems move with weight. When change touches millions or billions of people, even small steps become complex. Turning a very large ship takes slow, steady steering and constant checks to be sure parts hold under stress. The same is true for nations and networks. You cannot jerk the wheel without risk. You nudge, test, and hold the new course long enough for it to become stable. Culture adds another layer. Language, values, habits, and beliefs pass across generations like well-used tools. They are not rewritten by a single speech. People adopt new ideas through experience, trust, shared memory, and identity. The deeper the roots, the more energy it takes to shift them. Yet, they do shift. Civil rights, gender equality, and broad access to schooling advanced in fits and starts. Ideas moved from fringe to center as stories spread, laws adjusted, and daily norms caught up. At first, the motion was gentle and met with resistance at every turn. With steady pressure, the motion built. That is the other face of inertia. Once something begins to move, it tends to keep moving. Institutions can resist change, but they are not solid blocks. They are networks of people, roles, and rules. Under persistent, well-aimed pressure, cracks appear, policies update, and the default setting slides toward a new normal. Movements usually start quietly. One person speaking, one group organizing, one story landing at just the right time. Signals multiply, and a slow drift becomes a clear shift. History is full of such pivots. The end of legal slavery, the spread of voting rights, clean water and vaccination drives, protections for air and rivers, none came from a single moment. Each was a sequence of proposals, setbacks, court cases, boycotts, songs, research, and local pilots that became national practice. The pattern is not instant victory, but accumulation. Many pushes add up to a net push. Harmful patterns also persist. Inequality, exclusion, and corruption are not new. They ride on habit, fear, and misaligned rewards. But resistance is not always anger. Often it is uncertainty or lack of alternatives. Systems prefer the known path because the known path has working parts and trained people. Changing course asks for money, time, and trust. That is why stories matter. They put data into human terms. A clear narrative can slip past defenses, turn numbers into faces, and move the line between what is tolerated and what is not. Schooling plays a similar role. It teaches facts, but it also gives new frames for asking questions. It introduces comparisons and counterexamples that let people imagine different futures. Imagination is not a luxury here. It is the start of motion. Small policy updates, better forms, new checklists, more inclusive designs. These do not always make headlines, yet they stack. Over months and years, they tilt the floor so that better choices become easier choices. Sometimes inertia itself is the risk. Climate change, widening gaps in wealth, or failing public services do not pause while we debate. When delay becomes costly, momentum must be built on purpose. Governments can lead, but so can neighborhoods, firms, labs, studios, and small teams. Many small choices ripple, insulating a building, switching a bus route, cleaning a local stream, adjusting a hiring process. Each is a piece of net force. Progress does not demand perfection. It demands pressure that lasts. In physics, inertia is not apathy. It is mass. Large mass needs more force to change its motion. In social life, force is attention, votes, budgets, standards, shared goals, and time on task. If the world feels stuck, it helps to remember that motion often starts before it is obvious. Today's meeting can become tomorrow's pilot, next year's policy, and a new norm the year after. Quiet work accumulates. The idea of a net force ties these pieces together. In mechanics, the net force is the sum of all pushes and pulls that do not cancel. When the sum is not zero, acceleration follows. The same logic gives a clean way to think about personal and social change. As long as all efforts and resistances balance, nothing moves. When the balance tips, even slightly, motion begins. The picture is clear on a launch pad. A rocket sits still because the pull of gravity is matched by the structure pushing up. Engines light and build thrust. For a moment there is noise, but no motion. Then thrust exceeds weight. The net force points upward, and the rocket lifts. Slowly at first, then with growing speed. Nothing magical happened. The total push crossed a threshold. Daily life works the same way. Desire to change, a tool on the desk, a plan on paper. None of these move a habit unless the net of all supports and resistances favors action. Friction can be a late night, a crowded calendar, fear of failure, or simply an unclear first step. Lower those terms, make the first step small and obvious, and the same person often starts. Set a timer for 5 minutes. Place shoes by the door. Open the document and write one line. The aim is not to finish. It is to create motion, so inertia can help you instead of hold you. Groups follow the same pattern. One voice matters. 10,000 voices change the signal to noise. Votes, letters, pilot projects, and local wins add to the same side of the equation. In time, officials shift risk calculations, standards bodies update rules, and firms adjust products. The net force rises above the threshold needed to move a large, heavy system. Past movements make this visible. The civil rights era was not a single march, but many actions across years. Sit-ins, freedom rides, court cases, music, sermons, and images that made distant pain local. The environmental movement grew as measurements accumulated, science clarified risks, and cities tried new practices. Youth groups, business coalitions, and mayors joined. Policies followed because the total push had become larger than the resistance. Force does not have to be loud. It can be patient and precise. A well-designed default on a form, a clearer label, a sidewalk where none existed, a textbook example that adds missing voices. These are modest strokes that change flows because they act where people make choices. Many small changes in context make the new path the low-effort path. The idea also explains tension in relationships and teams. People promise change, and they mean it, but meaning is not force. Comfortable routines and old cues push back. A reason strong enough to tip the balance is needed care for someone, a hard boundary, a new constraint, or a new tool. Once the start is made, repetition turns effort into ease. Neural pathways strengthen with use. Activation energy drops. The same brain that resisted now helps you continue. Momentum compounds. In physics, acceleration increases speed. In practice, early progress makes later progress cheaper. A neighborhood that adds one safe crossing finds it easier to add a second. A library that makes one inclusive program can reuse the template. A company that redesigns one process gains staff who can redesign another. Each success reduces the next barrier and adds belief that the work produces results. Building net force is part design, part timing, part support. Clarify the first small move. Align incentives so the better choice is also the easier choice. Remove steps that slow the start. Add feedback that shows progress early. These are simple tools, but they are reliable because they match how motion starts in any system with inertia. Resistance never drops to zero. Old habits persist. Stakeholders disagree. Budgets tighten. People tire. These are forces on the other side of the sum. The work is not to pretend they do not exist, but to plan for them. Short rests prevent burnout. Backup plans keep motion during setbacks. Diverse teams find alternate routes when one path is blocked. Measured pace beats short bursts that fade. Not all pushes should be made. Inertia protects too. It keeps critical records stable, stops fads from overturning safety standards, and prevents sudden swings that would harm the most vulnerable. The art is to respect useful stability while moving what is harmful or out of date. In practice, this means testing before scaling, protecting core services during change, and listening to those who will live with the new pattern. There is a clean test for whether a push will help. Map the current forces. What keeps the state as it is? Habit? Law? Cost? Risk? Lack of alternatives? Which small inputs would reduce those? Which inputs would add to the desired side time? Saved? harm reduced, value created, trust earned? If the answer is unclear, start with pilots that measure effects. Data tightens the estimate of net force and lets you adjust. Signals matter as much as structures. A leader who shows up on time to a safety talk, a teacher who models curiosity, a manager who reads and replies to the first progress report. These seem small, but they move weight because they shift expectations. Expectations are a form of stored force in groups. When people believe an effort will last and be rewarded, their own effort adds to the total. When they believe the effort will fade, their energy becomes resistance. The frame also helps when motion is in the wrong direction. Harm can gather momentum. Misinformation spreads. Bad incentives reward the wrong outputs, or a practice that worked once becomes a liability. Here, the first step is to remove sources of push change incentives, correct the record, or stop the input that feeds the drift. Only then does it make sense to add new pushes toward a better path. Otherwise, you are trying to accelerate and brake at the same time. A useful image is a threshold. Below the threshold, effort feels like pushing on a wall. Above it, the same effort moves a load. Much frustration comes from aiming at the wrong part of a system or using tools that do not match the resistance. The cure is not more strain, it is better placement of force. In practice, that often means starting earlier, at smaller scale, in a part of the system that will not break when it moves. The small motion becomes proof and creates room for the next motion. Across physics and public life, the rhythm is the same. Identify what keeps the current state in place. Reduce unhelpful resistance where you can. Add steady, well-aimed inputs where they will matter. Expect a delay between push and motion, and keep applying the push long enough for momentum to build. Once motion exists, protect it from random bumps. Tune the path as you learn. The simple rule is not a slogan. It is a working method that fits how heavy systems behave. The point where everything is still often feels like failure, though it is usually a balance of forces. Slight changes to the sum a clearer first step. A matched incentive, a small redesign, a story that earns trust can cross the threshold. Acceleration begins not with a grand leap, but with an imbalance that favors a direction. A small imbalance can start everything. A little extra weight on one side, a steady pull in a new direction, enough to make the old path wobble and a new path begin. Whether it is a rocket leaving a pad, a person changing jobs, a community fixing a broken rule, or someone rising before the third alarm, the same question appears. What holds you in place, and what moves you forward? In the end, the rule does not bend. When the net force is not zero, direction changes. Time and patience decide when. Effort decides how. There is a quiet beauty in a universe that prefers to coast. Start motion and it continues. Remove the push and it does not fade on its own. Set something gently on a table and it remains. This is not laziness. It is consistency. The laws do not shout. They keep promises. Inertia honors what already is until a cause appears to change it. Another rule lives beside it. Entropy. People often call it disorder, but think of it as the spreading of energy. Heat flows from hot to cold, not the other way around. Coffee cools, toast burns, and a neat desk gathers stacks. Left alone, systems slide toward a kind of balance where nothing drives a change. Edges soften, differences even out. Entropy, like inertia, is not loud. It is a steady drift that only work can resist. Together, these rules sketch a calm cosmos. Motion is preserved, Structure needs care. Walk into an old, empty house, and you see the idea. The walls still stand, but dust lies on the floorboards and hinges rust. Not because anyone damaged them, but because nothing worked to keep them sharp. Without a countering input, edges round and patterns blur. And yet the universe is not dull. Stars form and die. Rivers cut rock. Storms rise. Cells divide. Black holes spin. The stillness is background, not the whole picture. What bridges the two? Motion itself is no problem for the cosmos. It simply does not change without cause. From the first moments, there was a cause. The early universe expanded. Space stretched. Energy and matter flowed. That first motion set directions that still echo. Galaxies spun up. Gas clouds collapsed. Stars turned on. The rush slowed and spread, but it never truly stopped. Today's quiet rests on ancient momentum. You can see this thread everywhere. A comet bends around the sun and continues out. A leaf falls, then slides along the ground until friction spends its motion. A thought once formed returns more easily the next day. A plan, once begun, meets less resistance on the second step than on the first. In each case, something that started tends to keep going until a clear counterforce appears. Drag, heat loss, doubt, a door closing, or a hand at the shoulder. Is inertia only a property of matter, or is it telling us something deeper about how time and cause work? One way to see it is as a kind of memory, not awareness, but continuity. A moving object remembers the push that set it going by keeping the same velocity until acted upon. A still object remembers its rest. History does not vanish between moments. In Newton's laws, in curved space-time, and in quantum fields, the present grows from the past in a smooth line. Things do not swerve without cause. They do not appear or fade without reason. Life fits inside this picture. A living cell holds order by spending energy. It pumps, repairs, and organizes itself against entropy's drift. A body keeps temperature, heals cuts, and remembers patterns of movement. Sleep, food, and air are not luxuries. They are inputs that hold a shape against the steady spread of energy. When inputs stop, order gives way. The change is not sudden chaos. It is a return to the default, which is stillness and balance with the surroundings. That default is not a failure. It is what everything tends toward unless work says otherwise. Still, we resist that slide in small, steady ways. We build tools and cities. We learn names for the sky and for the atoms under our feet. We teach the rules to the next group and ask them to test them again. Each lesson is a push. Each trial is a small force. Ideas add, some cancel, some reinforce. Over time, the sum reaches a threshold, and a new direction becomes the normal one. In that sense, a school, a clinic, a bridge, a satellite, each is a shape held against drift by continuing effort. Stop the work, and supplies, skills, and parts spread out. Continue the work, and the shape holds. Because inertia is neutral, it helps and it resists. It keeps a stable course when the water is rough, and it makes sharp turns hard when a turn is needed. It holds a useful routine in place. It also keeps an unhelpful habit alive. The lesson is practical. Measure the forces, not just the wishes. If change is hard, map what pushes back. Is it cost, time, fear, Friction? Missing tools? Reduce those where you can. Add steady inputs where they will matter: a clearer first step, a better default, a support that arrives on schedule rather than at random. When the net of all these pushes and pulls crosses the line, motion begins. With motion, continuation gets easier. Physics gives language for that feeling. Thresholds, activation energy, momentum. In a lab, these words point to numbers. In a day, they point to what it takes to start the file, to ask the question, to move the meeting forward one honest inch. Not every push must be large. A nudge at the right time beats a shove in the wrong direction. A series of modest, well-placed forces can do what one grand effort cannot, because they add with the grain of the system instead of against it. Seen across scales, the rules hold together. In space, no engine is required to keep a craft in orbit. A brief burn changes the path, and gravity does the rest. On a road, engines work constantly, because air and tire friction never stop. In a cell, pumps run to hold salt levels. Stop them, and diffusion erases the pattern. In a mind, repetition strengthens a pathway. Neglect weakens it. In a city, standards and routines keep water safe. Stop testing, and drift returns. The differences come from which forces are present and how strong they are, not from separate sets of laws. Entropy returns here in a gentle way. It does not say, nothing matters. It says, inputs matter. If you want heat to flow the other way, you must do work. If you want a neat desk, you must sort and file. If you want a plan to stay on track, you must check and adjust. Inertia says that what you begin tends to continue. Entropy says that what you build tends to spread, unless you care for it. Together they make the world predictable enough to build in, and honest enough to require effort. There is also comfort in knowing the universe does not change its mind at random. Without inertia, there would be no stable atoms, no orbits, no trust that a wheel will carry you from one corner to another. Without entropy, there would be no reason to eat, no clocks to wind, no weather to move heat and water across the planet. The same laws that ask for effort are the ones that allow structure to exist at all. So, the picture is not stern, it is steady. The rule is simple and patient. Keep doing what you are doing, unless something tells you otherwise. A bird glides because air provides lift and drag in just the right mix. A planet circles because gravity bends its path smoothly inward. A small idea carries because it catches on a few minds, then a few more, and then becomes part of the background. None of this is magic. It is cause followed by effect, motion followed by motion, change followed by a new normal. If there is a single thread to hold, it is this: states persist and causes count. When the state is good, protect the conditions that keep it. When the state needs to change, build the net force you need and place it where it will matter. Expect delays. Expect some loss to friction. Expect small course corrections. These are not signs of failure. They are signs that you are working in a real world with real rules. And if the scale of things feels large planets and galaxies, cells and cities turn the lens closer. Feel the slow spin of the ground under you, too steady to notice. Hear the small rhythm of your own breath, easy to forget. Notice how a page turns with the lightest push once it starts moving. The same laws cross all of this, tying quiet motions together. Out beyond the roofs and trees, the deep sky holds its lines. Orbits continue. Tides rise and fall. A faint trail from a satellite fades into shadow. Indoors, a mug cools by a few degrees, a clock ticks, a thought returns, then drifts. The patterns do not hurry, they do not stall. They carry on, the way they have all along, with a calm that asks nothing and explains much. Let the last images settle, a planet gliding, a leaf turning, a hand giving the smallest nudge, and let them fade to the background hum. The rules keep working, whether we watch or not. Night leans in a little closer. The room grows quieter. Motion, for now, takes a softer line.